Welcome class 7. This is the continuation video of the second chapter number system of the book ICSE Understanding Computer Studies class 7. In the previous video we have already discussed up to page number 27 octal to decimal conversion. In this video we will start from page number 28 octal to binary conversion. Let's start. Conversion from an octal number to a binary number. An octal number system uses all the digits from 0 to 7. We can directly write the equivalent binary of each octal digit by using 3-bit form as shown below. This means that octal number system has 8 primary digits 0 to 7, and each octal number can be represented by equivalent binary 3-bit code. Now the question is, why this 3-bit form? We all know that octal has the base 8 and binary has the base 2, and 2 cube equal to 8. So the power of 2 is 3. This is the reason that we can express the octal number in 3-bit binary equivalent. Here is a table. It contains all the octal digits on the left side and all the binary equivalent on the right side. 0, the first octal digit, can be represented by 0, 0, 0. Then 1, 0, 0, 1, 2, 0, 1, 0, 3, 0, 1, 1, 4, 1, 0, 0, 5, 1, 0, 1, 6, 1, 1, 0, and last 7, 1, 1, 1. Now let's start the octal to binary conversion. The first number is 312. It is an octal number. We just copy the number here and write its binary equivalent. Binary equivalent of 3 is 0, 1, 1. Binary equivalent of 1 is 0, 0, 1. And binary equivalent of 2 is 0, 1, 0. So the binary equivalent of 312 octal number is 0, 1, 1, 0, 0, 1 and 0, 1, 0. This 0 is a insignificant digit. So the final equivalent number is 1, 1, 0, 0, 1, 0, 1, 0. Now the next number. The number is 704 base 8. We just copy the digits here and then write the binary equivalent of each digit respectively. Binary equivalent of 7 is 1, 1, 1. Binary equivalent of 0 is 0, 0, 0. And binary equivalent of 4 is 1, 0, 0. So the binary equivalent of 704 is 1, 1, 1, 0, 0, 0, 1, 0, 0. Now the next conversion. Binary to octal conversion. The first example is 11000101. This is a binary number. First, we have to create a 3-bit group from the right side. So this is our first group 101. The second group is 100, and the third group is just 1. So we put 2 zeros here and create the third group 001. Now we just write the octal equivalent of these binary numbers. 001 is the binary equivalent of octal 1. 100 is the binary equivalent of octal 4. And 101 is the binary equivalent of octal 5. So, the octal equivalent of this binary number is 145 base 8. Now the second example, 1100 1100001. Again, create a 3-bit group from the right side. So our first group is 110, then 101, next group 001, and finally 11. Here we put a 0 and we make it 3-bit group. Now 011 is the binary equivalent of 3. 001 is the binary equivalent of 1. 101 is the binary equivalent of 5. And 110 is the binary equivalent of 6. So the octal equivalent of this binary number is 3156. Now the next topic, hexadecimal number system. In the hexadecimal number system, we use the digit from 0 to 15. This means that in hexadecimal number system, there are 16 primary digits, 0 to 15. But these digits are not available in the decimal number system. This means that the digits present in hexadecimal number system are not same as the digit present in decimal number system. In the decimal number system, only 10 digits are present. We already know that in decimal number system there are only 10 primary digits, 0 to 9. In the hexadecimal number system, the digits 10 to 15 are represented by alphabet A to F. This is the new thing, that in hexadecimal number system, the number 10 is represented as A, 11 as B, 12 as C, 13 as D, 14 as E, and 15 as F. So the base of this hexadecimal number system is 16. Now we start the conversion. Decimal number to hexadecimal number. Now the next conversion. Let's start the decimal to hexadecimal conversion. The first decimal number is 2699. We have to divide this number by the destination base. So we have to divide this number by 16. The quotient is 168 and the remainder is 11. And we know that 11 in hexadecimal is B. So here we write B in the place of 11. Next, again we divide this quotient by 16. The next quotient is 10 and the remainder is 8. Again we divide this 10 by 16. So the quotient is 0 and the remainder is 10. And the hexadecimal representation of this 10 is A. So we write here A. Now we get 0 as quotient, so we stop the division. The final hexadecimal equivalent of this decimal number is A8B, bottom up approach. Okay, we have to write this number in bottom up approach. So we write A here, first digit, then 8, then B. Now the second example, 58,823. It is a decimal number. First we divide this number by its destination base. So we divide this number by 16. The quotient is 3676 and the remainder is 7. Again we divide this number by 16. We get the quotient 229 and the remainder 12. And the hexadecimal representation of this 12 is C. So we write here C. Again we divide this 229 by 16. We get the quotient 14 and the remainder 5. Again we divide this 14 by 16. We get the quotient 0 and the remainder 14. The hexadecimal representation of 14 is E. So we write here E. Finally we get the 0 quotient. So we stop the division. And the hexadecimal representation of this number is E5C7. We have to write these numbers in bottom up approach. So E is the first digit, then 5, then C, and the last digit is 7. Now the next conversion, hexadecimal to decimal conversion. The first hexadecimal number is 7CE base 16. We just write the digits like this, 7, then C, then E, and then multiply each digit by the power of 16. But one thing is to observe that the power 0 is start from right side and then in increasing order it moves. Okay, so 7 into 16 to the power 7 into 16 square plus C into 16 to the power 1 plus E into 16 to the power 0. Now 16 square means 256 and 256 into 7 means 1792. Next 16 to the power 1 means 16 and the decimal representation of C is 12. So 12 into 16 is 192. And the last one, 16 to the power 0 means 1. 1 into 14. 14 means E. Decimal representation of E is 14. So 14 into 1 is 14. Now add these three and finally we get 1998. This is the decimal equivalent of this hexadecimal number. Now the next example, the number is ABC base 16. First we write the digits A, then B, then C and multiply this digit by the destination base and start the power of 16 from 0 from the right side and then write these powers in increasing order. So A into 16 square plus B into 16 to the power 1 and C into 16 to the power 0. 16 square means 256 and 256 into 10 is 2560. 16 to the power 1 is 16 and decimal representation of B is 11. So 11 into 16 is 176. And decimal representation of C is 12 and 16 to the power 0 is 1. So 12 into 1 is 12. Now add these three digits, add these three numbers, and finally we get our decimal equivalent, that is 2748. So this is the decimal equivalent of this hexadecimal number. Now the next conversion. Now the next topic. Conversion from binary number to the hexadecimal number. To convert any binary number to its equivalent hexadecimal form, group the binary digits in 4-bit pattern from the right hand side. This means that to perform the conversion from binary to hexadecimal, first we have to create 4-bit group from the right side. Okay, why this 4-bit group? As the base of hexadecimal number system is 16 and the base of binary number system is 2. And we know that 2 to the power 4 is equal to 16. So the power of 2 is 4. This is the reason that first we have to create 4-bit groups from the right side. Okay. You can add 0 to the left to make the number of bits into a group of 4. So we can add zeros in the left side to make this 4-bit group. Okay, if required. Convert each 4-bit pattern into a decimal number. So the second step is we have to write the decimal equivalent of these 4-bit numbers. Okay, let's start the conversion. Binary to hexadecimal number. Now the next conversion, binary to hexadecimal conversion. Our first binary number is 1100110111. First we have to create 4-bit groups from the right. So our first group is 011, then 0011, then 110. Here to form 4-bit group, we just put an insignificant 0 and form 4-bit group 011. Now hexadecimal equivalent of 0110 is 6. Hexadecimal equivalent of 0011 is 3. And hexadecimal equivalent of 0111 is 7. So the final hexadecimal number is 637, which is the hexadecimal equivalent of this binary number. Now the next example. The binary number is 11101111, then 00. Again we have to create 4-bit groups from the right side. So the first group is 1100, then 1011. Then we put two zeros here and form 0011. These two zeros are insignificant. So the number remains same. Now the hexadecimal equivalent of 0011 is 3. Hexadecimal equivalent of 1011 is B, and hexadecimal equivalent of 1100 is C. So the final hexadecimal number will be 3BC base 16, which is the hexadecimal equivalent of this binary number. Now the next topic, conversion from hexadecimal number to the binary number. We know that the hexadecimal number system uses 16 digits, 0 to 15. So we can directly write the binary equivalent of each hexadecimal digit from 0 to 15 by using 4-bit. We have already discussed that we can represent a hexadecimal digit in 4-bit binary code. Here is a table that contains hexadecimal digits in the left side and its 4-bit binary equivalent in the right side. 0 is equivalent to 0000. 1 is equivalent to 0001. 2 is equivalent to 0010. 3 is equivalent to 0011. 4 is equivalent to 0100. 5 is equivalent to 0101. 6 is equivalent to 0110. 7 is equivalent to 0111. 8 is equivalent to 1000. 9 is equivalent to 1001. 10 is represented as A and is equivalent to 1010. 10 in hexadecimal number system represented as A and its binary equivalent is 1010. 11 represented as B and its binary equivalent is 1011. 12 is represented as C and its binary equivalent is 1100. 13 as D and its binary equivalent is 1101. 14 as E and its binary equivalent is 1110. 15 as F and its binary equivalent is 1111. So the base of this number system is 16. Now the knowledge corner. Hexadecimal numbers are represented in alphanumeric form. We already observed that in hexadecimal number system, the numbers 10 to 15 are represented as alphabet and 0 to 9 are represented as numbers. So this is a alphanumeric number system. The next conversion is hexadecimal to binary conversion. The first number is ABC. This is a hexadecimal number. First we write the digits here ABC. Then we just write its binary equivalent in 4-bit form. So the binary equivalent of A is 1010 and the binary equivalent of B is 1011 and the binary equivalent of C is 1100. So the final binary equivalent of this hexadecimal number is 1010111100. Now the next example. The hexadecimal number is D97. We just write the digit here and write its binary 4-bit equivalent in this row. The binary equivalent of D is 1101. The binary equivalent of 9 is 1001. And the binary equivalent of 7 is 0111. So the binary equivalent of D97 is 110110010111. We have completed this chapter. In the next video, we will start another chapter. Bye.